Okay, so let's start with a quick summary of what we have done so far. And even before that, let me say something about what we expect our results for some observable to look like in a generic situation. So suppose you have an observable sigma. So sigma, you will of course do a perturbation theory. So you will have results coming out of your perturbation calculation. Okay. But in general, this observable will also have contributions which cannot be captured by perturbation theory. Okay. And that's going to be the very last thing that I arrive at, and to which this all the 3 lectures are actually meant about. So you will also have corrections, terms which, so let's say Q is the scale in the problem. Okay. Then there will be also terms which I write as some coefficients, and you will have terms of these forms. Okay. These are suppressed by powers of Q. Lambda is lambda QCD. It depends on your number of flavors you have. Okay. So these corrections of the form 1 over Q or 1 over Q to the 4 or 1 over Q to the cube square, these cannot be captured by perturbation theory, but the total result will have both the pieces, perturbative result, which is a series expansion in alpha s, and these terms. Okay. These are called power corrections. So first of all, these are non-perturbative. Perturbation part is here. We will also see why I am calling these as non-perturbative. Okay, what's non-perturbative about it? That will come later in the lecture. So these are non-perturbative and they are called power corrections. And you would be interested in knowing what is the dominant power correction that you have. Okay, whether it goes as lambda over Q or it goes as lambda over Q to the 4th. Okay. So you can imagine if your scale Q in the problem is not very large, then these corrections could be sizable. Okay. So that we have to keep in mind that this is what we are after actually. Now let's give names to certain things which we have discussed in the last 2 lectures, so that it's easy to refer to them. We have obtained expression for D, some coefficient here, not so crucial for what I want to say. And you recall this term was coming from low values of k or k tilde, right? So that's, it's cut off. So what should I do? I should, okay, I can, I think it's busy over phone. So, huh? It's okay, okay. You know, our brains are wired to keep getting distracted. Sometimes I'm preparing notes and this mobile phone I'm checking without realizing that I'm checking it. So that's, you remember this is what I was calling as DIR, contribution from infrared region coming from low values of K. And then we had a term I hope my factors are correct, but even if they are wrong, the point that I am trying to make is still fine. So we had these factorial growth coming from infrared region. This factorial growth is called IR renormalon. Okay. It's called okay, and this one is similarly called UV renormalon. Okay, if you have many of them, they are called UV renormalons. Okay, so that's the terminology we have for things which are growing factorially. And this was what we had in, I guess, first lecture. Then in the second lecture, we saw that in certain examples when we were looking at the solutions of differential equations near irregular singular points, that you get solutions which can give you asymptotic series. Okay? And even though the series is divergent and it does not make any sense to have very large number of terms included, you get something divergent. But we nevertheless saw that there was a very good agreement with the numerical computation if we were to include first few terms which were obtained by doing the asymptotic analysis. And it also got better as you included a few more terms, but then we also know that eventually it gets bad. So, and also we argued that the best estimate that you can get is by stopping at that term in the asymptotic expansion which has the lowest value. Okay? So you keep all terms before that, excluding this one, and that term which is the smallest gives you the estimate of the error you have. Okay? So this is where I think we had stopped, and we were wondering that if we knew all the terms in the perturbation series, if we had calculated all of them, okay, then is there any value in knowing all of those? Because it looks like you should stop there. Okay? So there is no information contained in there. And this is what this lecture is about. We will figure out what information is contained in there in a simple setting and then apply here. Okay? And then also we will answer our question why these are called non-perturbative and what we can say about such non-perturbative corrections. Okay? So, since the goal of these 3 lectures is not to give an overview of the field, which unfortunately I do not have, but to rather get you introduced towards the field, I will give you the references that I have been using and you can then follow these. So, there is a physics reports article titled Renormalons. By Beneke. Okay, he has worked extensively on this field, and physics reports, this is 317. Okay, it's also available on archive. And a textbook which will be very useful is, and actually very nice book, is Bender and Orszag. I have used that in my previous lecture. Okay, I should. So, this book is called Advanced, it is a nice title also, Advanced Mathematical Methods for Scientists and Engineers, and subtitle is asymptotic methods. So you can imagine it will have a lot of discussion on asymptotic series and related stuff. Asymptotic methods and perturbation theory, or in perturbation theory, I guess. Anyway. Okay, so that will be a very useful reference. So you can think like, what's the point of knowing all the terms in the series when I cannot use the terms beyond certain order? But you might also ask, when will that happen that you know the entire series? I'm not going to calculate infinite terms, right? So that question is also there. So we'll come to these towards the end, but let's first proceed. Okay, so what I want to do really is sum the divergence series, and of course not the naive sum of adding up terms, but something little smarter. The name of this is so I am looking at a particular kind of summation called Borel summation. For different kind of divergence series, you can also have other kinds of summations, like I think one is called Euler's summation. I am talking about a specific kind. So let's say you have a series which is I could have used alpha, it would have been better. So think of x as alpha s, okay, but let it be like this. Suppose that's a series which is factorially divergent. Okay, that's the situation we had for D. So I define a function, a new series I take the same thing, a n, x to the n. I know there is a factorial growth, so I divide these coefficients by n factorial. Okay, and I have a new series. Suppose it so happens that for small values of x, this series is convergent. Okay, then this exists. So suppose this converges for small x. Now let's define an integral, okay, which will be a function of x like this. So that's the series we have, divergent. I have defined another series which is convergent by dividing the coefficients by n factorial. That's a convergent thing. I take that function, okay, which is convergent for small x, so it's some function. Take that, okay, multiply with some t, scale it by t, and integrate this from 0 to infinity. Okay. Now let's see what this integral looks like.
Excuse me. So why this rule of x is coming in the phi of x, like this small x? Our series was initially like, why there is a rule of small x? You are saying na ki it converges for small x. Why you put it there? I mean,
are you trying to connect to alpha s, like?
Yes.
Is that the question?
Yes.
Yeah. So if you don't like, let's call alpha s. Okay. So everything will be alpha s. Is that okay? I'll go back to S because in my notes for some time it is X. Yeah, I should have done that. It would have been easier. So you understand, right? Right now I'm not just thinking about Q series, any series. I'm doing mathematics. So X is alpha S for you. Okay, so I have defined an integral using this one. Now you can check, it's an exercise, I will recommend to have a look at the book, but nevertheless steps will be fine here, but if you need to convince more yourself, then you have to refer to the book. So this is this function, this integral is asymptotic to what I write here. So it's asymptotic to, I'll just write it first. So I'm just substituting this expansion here. Okay, that's what. So phi xt, I just here put xt, and this thing I put here, and take the sigma summation outside the integral. That's all I am doing. Is that okay? That's phi xt I am substituting, that's an over n factorial, that's here. X t to the n, it should become x to the n is here, t to the n is here, and then it's e to the minus t, and then that's the summation. Okay. So claim here is you have to use a lemma to argue that this is this function, this integral, this function bx is asymptotic to this expression. Okay, because what I am giving you is a series now, and I should argue that this function is asymptotic to that series. Okay. So now this is, so bx is asymptotic to, I will do integration term by term, and what do you get? What is this integral? It's gamma of n plus 1, it's n factorial, and you have n factorial below, so that cancels, and you get a n x to the n, right? So see what has happened. I had a divergent series. I defined a function by dividing the coefficients by n factorial, then I define some integral, and if I take that integral, which is a function, and I do an asymptotic expansion, then I get the original series, right? Which means I could define the sum of this divergent series to be that integral, because after all that is asymptotic to that series. So even for those values of x or alpha, when your divergence series doesn't give a finite thing, if you naively add it up, okay, you have a function which you can assign it to. Okay. So this is called Borel sum. So b of x is called the Borel sum. Borel sum of this series. Okay, and you can check that if you take, let's say you take 1 plus x square plus x cube and so forth, which is, right, it's convergent for mod x less than 1. Okay, that's converges, which is, I mean, this is 1 plus x square and so forth. This is convergent for x less than 1, and you know that the sum is 1 over 1 minus x, but you could do this procedure and arrive at the Borel sum, and you will get 1 over 1 minus x. Okay, so that's, now that is true for all x except for x equal to 1. So yeah.
in this previous derivation of the equivalence of the Borel sum to that asymptotic series, did you really use the fact that an diverges factorially? You just divided by n factorial, and by the definition of bx it cancelled out.
So even if it does not diverge, as I'm giving an example here. So here the coefficients are not, they are 1, they're not divergent, right? If you apply the same procedure, you'll get 1 over 1 minus x. You'll get a sum.
Yeah, so I mean this derivation is more general for any factor, like any divergence.
Yeah, if you had very bad kind of divergence, even worse than factorial, then this might not work.
But I can't see that from the derivation, or is that?
Yeah, because I assume that this is convergent for small values of x.
Oh, right. Okay.
Okay. And also here, from here to there, there is a lemma that has been used, and things might go wrong there. Okay, so that's the place where. Okay, so now we are able to give a function which we can claim is the sum of this divergent series. Okay, so that's where we are. So now what we are going to do later in the lecture, I will make a slight modification. So suppose I have instead of using a next to the n, I will just have rather, so x I should have used it, I will have alpha or x to the n plus 1. Okay. Sorry for again changing notation, just telling you copied from different places. So, okay. And this doesn't affect anything. You can have instead of alpha s to the n or x to the n, alpha n plus 1, and that will still be fine. So, the nomenclature that I am going to use is, suppose you have some observable r which is asymptotic to this series, okay, then this step, this thing we will call as Borel transform. Okay, so you do a transformation which is dividing the coefficients by n factorial. So we say we take a Borel transform of this series, which depends on alpha s, which was x earlier. Okay, same thing, and then by r tilde I will denote the Borel sum. It's the same thing as before. Instead of using xt, I am using t, and that's why you have a t over alpha here. Okay, so I've just changed the variables. You can check. So this is Borel sum or Borel integral. And you can check that using that you will generate the original series. Okay. So now let's go back to the d function that we had and recall, I think you can, maybe you can look at your notes, it's all these things and there is summation over n, and you have alpha s to the n plus 1, and there are some coefficients minus beta naught f over 2 to the n and factorial, and then the other term has, in addition to some coefficients here, just a second, and then another term, this is alpha s to the n again, or n plus 1, and you had here n factorial and some things. Okay, yeah.
Shouldn't be there n plus 1, alpha raised to power n plus 1?
Where?
The the transformation you.
Here?
No. Yes.
This one?
Yes.
Yeah, I think so. That should be correct. Yeah, it should be. Or let me see. No, looks like not. No, so this was correct. So I have this algebra in my notes, and unless I made a mistake in algebra, it comes out fine. So if I plug it in here, I think that extra alpha s you are seeing, that gets compensated by there. And
Okay,
not by here.
okay.
Actually, when you just do the change of variables, there will be 1 over alpha s sitting there, and that is compensating. So it is fine. It is this way.
Okay. Thank you.
So these are the terms which we had in the D function. So it's telling you the kind of coefficients you have in the series. So the coefficients are of the form some constant k, some constant a to the n, which in this case, for example, is minus beta naught half over 2, and in that case a is beta naught f, okay, raised to the power n. And then you have gamma of n plus 1 plus b, where b is greater than 0. So here you have n factorial. So if I put b equal to 0, gamma n plus 1. Here you have n plus 1 factorial, which means b is equal to 1. Okay, so n plus 2, gamma n plus 2 is n plus 1 factorial. So you see that the coefficients R n in the series, they are of this form. Agreed? That's what we are seeing. So our goal is to see if I can provide a sum to this D function, okay, a Borel sum to this, so that I have summed up the entire divergent series. That's what I want to do. So step 1 would be to do a Borel transform. Okay, let's do it. So that's summation n equal to 0 to infinity. All I have to do is take the Rn's and divide by n factorial, right? So you have Rn is this, k a to the n b, and then you divide by n factorial, and you have alpha s to the n, okay, where b is greater than 0. Is that okay? The step is clear that this is what we should do first. I have a series, D is sum of series which are factorially divergent. I first divide all the coefficients by n factorials, that gives me the Borel transform, then do the integral which gives you the Borel sum. Okay, so I am doing Borel transform now. So B is k a to the n, and the gamma function I will start with, okay, alpha s to the n over n factorial that I have. Then gamma function, gamma n plus 1 plus b, I will write as gamma 1 plus b. Okay, and if I multiply 1 plus b, it becomes gamma 2 plus b, and you keep multiplying, okay, till n plus b. So that gives you gamma n plus 1 plus b. Is that okay? So gamma 1 plus b times 1 plus b is gamma 2 plus b. Okay, let's multiply one more factor. Then gamma 2 plus b times 2 plus b, that is gamma 3 plus b. And if you continue like this up to n plus b, you will get gamma n plus 1 plus b. That's what you have here. Okay. So this is a to the power n, because you see what kind of terms you have in the coefficients you have. You have, apart from this, whatever is there is what we are calling Rn, right? So that's some constant raised to the power n. That's some constant raised to the power n. Okay.
Okay.
Is it fine? So what do we have is k times gamma 1 plus b summation a to the n, sorry, here I think this is what you meant, a to the n alpha s to the n over n factorial, and then n plus b Is that okay? Yeah, this looks fine. Or let me change this also to a times alpha s to the n. Okay, think of a alpha s as some z to the n. So z to the n over n factorial times this factor. Can you see what the sum would be? I can see because I know the result, but can you see? So let's say b is 0. If b is 0, then that's 1 plus 1 times 2 times 3 times up n. That's n factorial. N factorial by n factorial divided by n factorial gone. You have just z to the n alpha s. So that's summation z to the n. That is 1 over 1 minus z, right? So this will be something similar, and I'll just tell you in a moment what it is. Okay, on the sides. So take this function f of z as 1 over 1 minus z power 1 plus b, okay, and I just do a Taylor expansion. So nth order coefficient in the expansion will be the nth derivative of this. So when I do the first derivative, I get minus of 1 plus b, and this increases the power by 1, but then there is a minus sign here that kills the minus sign. When I do differentiate it again, you generate 2 plus b, and this goes 3 plus b, okay, and again minus sign gets cancelled because of this. So you see, every time you differentiate, you start generating. So you start with 1 plus b, next time you differentiate 2 plus b, and so forth. These are the coefficients in the Taylor expansion. So I hope you are convinced that the sum of this is 1 over 1 minus z, and z is a alpha s. Agreed? I have just done a Taylor expansion. So f of z is equal to this is what we have, and you see here that n factorial is also there. So this is the sum, this is the Borel transform, okay. Now to get the Borel sum, I should do the integral of the Borel transform with that exponentially damped factor, and that will give me the sum of the series, okay, or the Borel sum of the series. Is that okay? Remember when I had earlier, I think last time I had written the expression for D, I had pointed out to you that some of the terms, There are like 3 series in it. It's gone. I think one of them has minus beta naught f. The other one has beta naught f to the n. So one is alternating series, another one is not. And now we are going to see why that is relevant. Okay, now it becomes very relevant for us. Why the series, the behavior, the change in behavior due to those. Okay. So maybe I'll summarize because I have said many things. We have seen that D, which I am calling in general R now because it is not specific to just D, you have a series which is of this form. Okay, that is the kind of series we encountered here. Then I said, okay, I will take a Borel transform of this, which is just creating a new series with the coefficients divided by n factorial, and I found that to be that result here. And now we want to do the Borel sum, which is is everything okay, or this is okay. Okay, we will take, sorry. Yeah, thanks. B of R. I have been saying that I have a series which is, let us say I knew R, suppose I knew R and it is asymptotic to this series. So that is the R in there, okay. Okay, now you might be happy that no, I will do the integral and I will have a Borel sum, right, and we would have summed the series. But it might happen that you have a singularity sitting on the contour of integration, right. You are integrating from 0 to infinity, you have your contour running along the t axis, and if your integrand has a singularity sitting on that, then the integral is not defined and your Borel sum is not defined, right. And that is why you see that remark about noticing these signs is important, because you see what is there, that is AT. The sign of A will tell you whether the singularity lies on the contour or not. So if A is positive, the singularity is at 1 over A. So singularity is at 1 over A. If A is positive, then the singularity is sitting on your contour. But if A is negative, then the singularity is not on the contour, it is on negative axis. So you are fine, right. So let us see, okay. Here A, which is minus beta naught f over 2, so beta naught f is positive, okay. So this is negative, and these terms which are IR renormalons are sitting on the negative axis, so there is no problem, okay. And these ones UV renormalons, they are giving you singularities on the positive axis, so you cannot have an answer, right, because there is a pole there, there are singularities sitting on this, okay. So that is what we should worry about. So I will Is this okay up to here?
Other part I want to see, but can
Which part?
1 minus 80.
Okay, he's busy with phone, so. He's deep in mobile phone. Can you? Okay, so I'm suspecting a wrong person. Someone else who's looking here is not realizing. Okay, sorry. So, is that okay now? Did you miss some part because of that thing? I can go through again.
கேமரா திருப்ப சொன்னா
Okay, so
திருப்ப முடியாது டைரக்டா கேக்குது
what I was doing? Correct. So, what you have is this. So, Borel transform of the Adler-D function, okay, is equal to all these other factors I hope there is no mistake, 2 plus beta naught f times t, and then some other pieces plus some factor here. Okay, agreed? That's what we have. Because one of the terms had n plus 1 factorial. No, n plus, yeah, 1 factorial. So that b is equal to 1, and that's why you have 2 here, and the others had n factorial, so that's why you have this. Okay, so that is coming from IR, and these are coming from UV renormalons. And now I should do the integral to get the sum. So at this stage, the singularity in the Borel plane, okay, we are doing complex integral over the complex plane. So you are in this Borel plane, and that's the integration contour. And we see now that the IR pole is sitting at t equal to minus beta naught f over 2. Again, beta naught f is positive, and UV ones are sitting at, sorry, 2 over beta naught f naught, and these are sitting at 1 over beta naught f. Okay.
Factorial behavior, right?
Yes.
And also the fact that the beta naught has a positive value or something like that.
Beta naught f. So I am
Being a positive value, and then also that original series has a factorial growth.
correct. Yes.
So it's still ill-defined even after Borel transformation, and
After
then bringing
Borel
back to inverse Borel. Basically, you do if you have a divergent series, you make a Borel transformation, and then do the inverse, right?
No. So I have a divergence series. Okay. I do a Borel transform, which is just dividing the coefficients by n factorial, and then I do a sum, which is integral, Borel integral. The thing is, if you take that integral and do an asymptotic expansion of this integral, it gives you the original divergence series. So that is why it's sum. What we are seeing here is that this integral, now I have to evaluate to give you the result. But I am saying that I cannot do that integral, or integral is not defined because there are poles sitting on the contour of integration.
That's reflection of the series as a specific.
That's so. Let's see here. This one is coming from IR, and that corresponded to, if you go back to alternating series, it had coefficients minus beta naught f over 2 to the n. These ones had non-alternating series. So the coefficients were going as beta naught f to the n without a minus sign. So where the poles are located, they are reflection of whether it's an alternating series or non-alternating series. That is what information is here. Okay, something else should have happened. Okay, good. So we are here. Now you say, okay, this doesn't bother me. There is a singularity here. That's my contour integration. I will just make a detour. Okay, and then the integral is defined. Or I could do a detour below. Indent the contour, go downwards. There's another integral. The two integrals are different, and there will be the difference between these two is captured by the pole, the residue of the pole. Okay, so let's say B is 1 or 2 or 3. So the residue is capturing the difference between these two integrals. Okay, so integral is not defined; it's ambiguous, but the ambiguity that you can figure out. Okay, so the imaginary part of that ambiguity is just captured by the pole, half of it. Okay, so you just use residue theorem, and we'll get what the ambiguity is in your this integral, okay, in the Borel sum.
Excuse me. So actually one naive question. So is there any correspondence between these poles and the divergence was coming in our original series?
Yeah, because of that only you have, yes. As I said, see, you had n factorial divergence, okay. Because of the factorial divergence, you are getting this Borel transform. Some of those, so you had three series, right, basically. One is n factorial, another is n plus 1 factorial, another is n factorial. These are the results after Borel transform. The only thing different between these three, as far as the location of where the poles are on the t-axis, is connected to what the coefficients were. Whether the A which was beta naught f over 2 in one case, and another case minus beta naught f over 2. Okay, so difference is only coming from the sign of whether the series is alternating series or it's a fixed sign series. Is that okay? So if the coefficients were fixed sign, you get this one, which is leading to poles here. So imagine you had a series where all those all the things were non-alternating, then you would get only this. Am I doing other way around? Okay, and then all the poles will be on the negative axis, and your integral is well defined. There is no problem. Okay, or if you had none of these, only those, then all the poles are on real axis, and your integral is not defined. So you indent the contour and say, okay, I have two results depending on how you indent, and there is a ambiguity in that.
It's not guaranteed that it is not summable or something.
Yeah, it depends on, as I said, suppose you had this situation where all the poles which are coming are on this side, then there is no problem. You do the integral, you will get a result. Does that answer your question? Okay. So let's look at the ambiguity then. I did it in the morning, so it should be somewhere here. Okay, maybe I'll just give it as an exercise. It's just looking at the poles. So, okay, let me first write the answer and then you can say. So I have been calling, where is that? This let's call R tilde. The Borel sum I am going to call R tilde. So the imaginary part of R tilde, which is coming from this indenting the contours this way or that way, you can check, and I'll also so this one. Let's say B is equal to 0, then you have a pole at t equal to 1 over a. So when you calculate the residue, you put t equal to 1 over a, so you have e to the minus 1 over a alpha s, right. So let's put B equal to 0, e to the minus 1 over a alpha s, and there is some 1 over a coming from when you do the change of variables, okay. So, and for a generic B you can write, you can have double pole or triple pole. So that's the ambiguity. How am I doing with time? 20 minutes. I always ask it this time, 20 minutes. So whenever I ask, he says 20 minutes. So it looks like either I am asking exactly 20 minutes before. Okay. No, I am just saying it's a coincidence. Third.
Exponential part looks like the instanton action, because apart from this factor of a is like
It's
1
a
by
non-portability.
g square, yeah.
It's a non-portability. Correct. So, yeah, you're spoiling my fun, Ravi. You're spoiling my fun. Yeah. Okay. But you are exactly. That's what I'm about to do. Is that okay? Are you with me up to now? So what does it mean? It means that what I said in the beginning, sorry to stop you from your remark, but it's exactly what you're saying I'm about to say. So remember I said in the beginning, you have an observable sigma, you do and it will be a sum of two things. It will have these terms which your perturbation theory cannot calculate, okay, and then you have a perturbative part. And you are also going to see why I say this perturbation theory cannot calculate, okay, why that claim is true. So in a moment you are going to see, but then if you are willing to take it, that you have a perturbative part and a non-perturbative part, which is power, these are called power corrections, right. So these are powers of lambda over q to some n, there could be several terms with different values of n. So what I have seen now is, if I take my perturbation series very seriously and keep calculating, it's divergent, but if I try to sum it up, I still don't get a unique answer. I get an answer which is ambiguous. It's something plus an ambiguous part, okay. But your sigma is non-ambiguous, it's an observable, it has to have one answer, okay, it cannot have 2 answers or 10 answers. So thing is, this part will also be ambiguous, and the ambiguities between the two will cancel to give you a well-defined answer, which then means if the ambiguities are going to cancel to give you a well-defined answer, then summing up the entire series is giving you a handle on the non-perturbative effects. After all, that ambiguity is of the form of lambda over q to something, and that's going to cancel ambiguities in the non-perturbative parts. So summing up this series, so your perturbation series also knows something or maybe a lot of things about the non-perturbative parts. Is the claim sounding reasonable? That's
This is only-
ambiguous. That's ambiguous. The sum is finite. which means the ambiguity here has information about the non-perturbative part.
This is assuming that your series is Borel summable.
No, I am not assuming that. If it was Borel summable, then you would have gotten a fixed answer, but you have not got one answer, you got this answer or that answer depending on how you indent the contour. So no, I have not
No,
been able
I
to.
was mentioning that your point that the non-perturbative piece, the ambiguity can account for the ambiguity in the perturbation series. That is only true when you can show that the perturbative part is Borel summable, right?
So I am not sure what you, so if there is a pole here, I would say it is not Borel summable. I think there is a different choice of words. So when I have a singularity here, I would say it's not Borel summable. Do you mean the same thing or?
Okay, you cannot calculate the integral, but you can write it this integral form there, right? As 1 plus a times t.
Yeah, but it's not defined. The integral is not defined.
Yeah.
If you have a pole, if you have a singularity on the contour, the integral is not defined. So you can say, okay, I have another integral by indenting up or down, but those are not the same integrals as before. Does that answer your question?
Yeah.
Okay. Okay, so okay, let's look at the ambiguity. If there was no pole on the real axis, I would have summed it up, but that's not the case. So it's not, I cannot sum it up. So the ambiguity that's written here, that imaginary, yeah. So the ambiguity is proportional to, so let's say b equal to 0, the case of n factorial, okay, but you can keep that also, is e to the minus 1 over a alpha s. A was what? Beta naught f over 2 or these kind of things. So, sorry, 1 over, these are the poles, right? So you get 2 over, please check that this is correct. Now I am looking at IR poles, right? UV poles are here on that side. IR poles are here. So beta naught f. So T is minus 2 over beta naught f. Okay, that's the, sorry. Beta naught f is positive. Huh. Yeah,
Recall it, you put minus.
I think that is,
You put minus 1 by 4 pi. That's 11.
Yeah.
11 over 3 ca.
did I make a mistake in sign or? Minus 1 over, yeah, so that actually I am going to use that fact. So right now I am with beta naught f, correct, that's good. So A is, okay, I think I understood what happened. I'll just write down. So what I'll do is, so beta naught is negative, so I am going to, I think that's why there is a problem here. So till now I have been just working with fermionic loops, okay, and I have been just going along with beta naught f. But now I will make a claim for which you need a diagrammatic explanation, and you can refer to Beneke. And the claim is, I can take beta naught f and replace it by beta naught, okay, that is justified, and there is an entire section devoted to it. So I will just make this replacement. But the thing is, the signs of beta naught f and beta naught are different. Okay. So when I make that replacement, I am looking also for the contributions of other kind of loops inside, and also the vertex correction, right, because beta naught will have that also. So, but the justification you can see, and this is what I have. And because of the sign difference, now it is fine, and beta naught is negative. Okay, so this is what we get. Is that okay? I have moved beta naught to beta naught f, sorry, beta naught f to beta naught, which also means the IR divergences, which were earlier on the left, on the negative axis, and the UV renormalons, which were sitting on the positive axis, they get swapped. So, UV ones go to the negative axis, and the IR ones come on the contour of integration. Is that okay? Because of this change, but that can be justified, and please see the relevant section. So, now you have IR renormalons. So, I am using renormalons for both that n factorial thing and the poles also same. So, IR renormalons, or let us say poles, okay, let us call renormalons, are sitting on the contour. Okay, which means they are going to give you ambiguities of this kind. These ambiguities are coming from there, not from the UV ones, because for UV you do not need to indent. Okay, good. So, now let me choose the scale mu square, renormalation scale of the order of q. Okay, or let us just identify it, choose it to be of the order of q.
Excuse me. So actually, my question is, why you didn't do this replacement before doing contour integration? You could have done that also, no?
Which replacement?
This replacement in the sense like beta naught f to beta naught, you are saying, right? Here.
It will not change anything, right?
No, then your pole
Yeah.
will be swapped, and
Yeah, it will be swapped, and that is what the claim is.
No.
They get swapped.
So initially your your UV had this double pole, right?
See, what is beta naught and naught, we do not know. Let us say we do not know what it is, some name, and you say based on this the poles are here and there.
Correct.
Depending on the signature, that symbol would tell you either the pole is on this side or that side. So, when you replace it by beta naught, your poles, IR poles are on the real axis. It does not matter whether you do before or afterwards.
No, if like UV pole on the negative side and IR pole on the positive side, so if you do the contour integration, initially it was double pole for UV, because there is 1 upon beta naught t to the power square, something like there is. So before doing contour integration, that IR will have only
Okay, so-
singular pole,
Okay.
single pole.
So, let us make life simpler. If you prefer, you do it beforehand. So, you say, okay, I am looking at all the contributions, and beta naught has to be replaced by beta naught f has to be replaced by beta naught, because I have all these diagrammatic arguments which justifies this replacement. Then you take the Borel transform, you get that thing, and now you are doing the integral. Is that okay? Okay, so let us choose. Okay, I have ambiguity of this form, and now this is, now we are at the important part. This ambiguity, in this ambiguity I identify mu square to be q square. You can take these scales to be same, and now recall, and this is what Ravi was saying, that if you take alpha s and look at the expression of so relate alpha s at k square to another scale mu square, okay, this is this, which you also know can be written as, okay, that is how you define lambda QCD, right. So k square. So what do you have? You have, let us take that beta naught to that side, beta naught alpha s at q square, sorry, k square is 1 over log of lambda square over k square. Now let us put this expression with this is lambda QCD, okay. Take it here, put it in this. So you have 2 over this part, so it is 2 over, what is that? Yeah, I will just write down that expression. You can already probably see the power correction which I wrote earlier coming out. So you have ambiguity is equal to, so I just substitute this in here and you get is proportional to, for this particular observable, that is to the 4, okay, that you already have squares here, that is a factor of 2 that goes makes it 4. Okay. So these are the corrections or power corrections that you get. Now I had claimed earlier that these are the corrections that you will not get, not generate from perturbation theory, right. So that is why I say these are non-perturbative things, and you see why. This is what has become power correction, right. This is exponentially suppressed term. So you have e to the 1 over alpha s, and it has a essential singularity at alpha s equal to 0. So you see this does not have a series expansion in alpha s, but when you do perturbation theory you are doing a series expansion in alpha s. So such terms cannot be generated by perturbation theory, and so it is clearly something outside that scope and it is non-perturbative, but that same non-perturbative thing using this appears as lambda over q. So clearly that is non-perturbative. So my original claim here that the thing is here is perturbative and then terms which are non-perturbative, and but they also have this form, was based on this observation, right, that this is a non-perturbative part. Is that okay? Okay, this has an essential singularity at alpha equal to 0. So what I am trying to convey is, at some point I said that the observables will have a perturbative component, meaning that you can calculate using perturbation theory, and some things which cannot be calculated using perturbation theory, and I said this will be the form. They could have logs also, but how do I know that this claim is true, that these are non-perturbative, and that is what I am saying. So you see here, this is what is giving that form, but if you look at this, this does not have a power series expansion. If you cannot expand it around alpha is equal to 0, okay. So this has an essential singularity, and when you are doing perturbation series, it is a power expansion. So that is how I was connecting it. Okay, so being able to figure out the ambiguity will give you a handle on non-perturbative parts. More crucially, you will not be able to get the prefactors here, but the power is also important, that you will be able to get, okay. Higher part, correct.
You don't have any non-perturbative part from UV part.
Yeah, UV will not give you power corrections, that is what it means.
Power correction, okay.
UV will not give you power corrections.
But there will be some non-perturbative part from UV side also, is that?
Yeah, but I will not be able to answer it properly, so I will avoid, yeah. So is that part okay? I was about to say something, I forgot. Okay, so you have gotten some handle on this, and the crucial part is the power, because you see if Q is not very large, then the power corrections become significant, okay, and then there is an interplay between perturbative and non-perturbative, how much precise you can say. And also these estimates if you get, you can use them to make models for non-perturbative effects. You say, okay, my non-perturbative effects are going to go as lambda to the lambda over q to some power, and then you could make a model and then fit with your results with experimental data. Okay, so those things you can do. Now you might still be wondering, if I cannot generate all the infinite terms, meaning I do not have the series, then I do not know what the Borel sum is, Borel transform is, I do not know where the poles are, right. So, all that is still there, and then how do I say anything? Okay, so, unless you have this infinite series. Now, in some cases you can have infinite series. Imagine you are looking at E plus E minus going to QQ bar, okay, let us say an event shape variable, thrust or C parameter or whatever, okay. And you have one soft gluon emission. Okay, or even collinear. Let us stick with soft gluon. But you know that soft gluon emissions exponentiate, okay, which means you have a handle over the entire perturbation series because of this exponentiation. You do a first order calculation and you are able to tell pieces or the dominant pieces at every order in perturbation theory, right. So, you generate entire perturbation series. So, that is what you do when you are doing resummation. Okay. So, you have that entire perturbation series. Now, what you do is you put bubbles in here, okay, and now you do the summation. So, you are now including the effects of these bubble diagrams and having soft emissions, infinite number of soft emissions, and you are you know those coefficients, right, to all orders. So, now you sum it up. Are you following the logic? So, what I am doing is I am generating an infinite series for you from these special configurations, okay. And now you generate that infinite series, do a Borel sum, do a Borel integral, find all those ambiguities, and then you are able to say, okay, these are the dominant power corrections that I will get for, let us say, even shape variables. No, why not? Why not? You have these corrections, right?
We have this LSZ formalism which says that when you equate the matrix element with the cross section, you need to impute.
Yeah, that will enter through Z. See, the result is you have to take all the diagrams, right? That enters through the Zs. So, they are still there. So, you will be able to then generate that entire series and sorry. Those also, yes. So, I am just giving this diagram. What Ravi is saying is this kind of things, okay. But I think I have made my point that even though the series is divergent, so first point was what I wanted to convey was, even though the series is factorially divergent and naively it appears there is no meaning to giving a prediction, but our earlier experience said that if you stop at to some point, your results make sense. Now, I do not know up to where you should go because you do not have the entire series, okay. And the second point is, even though you will not be able to sum up the entire thing because you will have poles on the contour, the result will be ambiguous, but that ambiguity is giving you handle on the non-perturbative effects. So, that is also very useful, and then you have the entire literature to explore. I know only this much. Okay, so I will stop here.